Matt and Brad pull a toy train with 2 coaches with a horizontal force of 10 newtons. The mass of the string that joins the coaches together is insignificant. B experiences a maximum frictional force of 0,7 newtons. So, the first one is sketch a free body diagram indicating all the forces acting on the 3 kilogram coach. Label all the forces clearly. So we're going to, that one, you can't just write a value, you've got to write frictional force. This forward force over here is an applied force. And of course it is a free body diagram, so it needs to start with a circle and then the applied force and then the frictional force. Don't forget that there is definitely a weight or a gravitational force, which is exactly equal to the normal force. And then, of course, there is still the tension in the rope. So there are 2 backward forces that are exerted on this particular little trolley. Will coach A experience a frictional force of 0,7 newtons? Explain your answer briefly. The answer is no, because remember, and it's always nice to use an equation in maths, so at least in science. So you're going to say the frictional force is equal to mu F normal. And we know that because this has a smaller mass, it will have less weight and therefore a smaller normal. And therefore, when you put a smaller number in there, even if the coefficient of friction is the same, your frictional force will be less. Diagram below shows a horse exerting a force on a cart. The cart accelerates on the tar road and the coefficient of dynamic friction is given. Calculate the resultant force acting on the cart. Force resultant is just equal to, mass times acceleration. We've got 100. We know it's accelerating at 0,5. So we get 50 newtons. And ideally you should have said right. I didn't take off a mark there, but it doesn't say the magnitude, it just says the resultant force, so it has a direction associated with it. The next thing is calculate the magnitude of F1. In other words, what is the force that the horse is exerting on the cart? So there's the force that the horse is exerting onto the cart, and then of course there is some or other frictional force over here. So force resultant is equal to the big force, the horse, minus the small force, the friction. We can work out the friction. Frictional force is equal to mu Fn. And because this isn't on an inclined plane, we can simply go 0,0. Oh, this changed to 0,02, didn't it? Sorry. 0,02 times by 100, 9,8. And that was equal to 19,6. Now I substitute that in. We know the force resultant is 50. We know the frictional force is 19,6. And therefore I am able to work out F1. And F1 turns out to be 50 plus 19,6. And that turns out to be 69,6 newtons. If the horse was pulling the cart over a dirt road, would it be fair to expect the horse to produce the same acceleration? Briefly explain your answer. And again, you want to use a calculation. So no is your answer. Mu on a rough road would be greater. In other words, the coefficient of friction. If you've got the same applied force, the greater mu would mean greater frictional force, and therefore less acceleration. We've now got this situation. As I said, the first thing to do is to try and work out what really happened before trying to explain everybody's faults in the situation. So the first thing to do is to say, I'm going to break this into its components. So first the perpendicular component is equal to 50 sine 30, which is equal to 25 newtons. And that's because it is the opposite side if I were to complete that triangle over there. And then the next one is to say, what about the normal force now? So if I have got big minus small, force normal plus this 25 newtons plus F app perpendicular must be equal to F grav. In other words, all the upward forces are equal to all the downward forces. So I am going to say F normal is equal to 100 minus 25, and that turns out to be 75 newtons. Now, it says here that Matt suggests that the normal force is 50 newtons. Well, 50 newtons, he's just taken this applied force and used it, which is not acceptable. So he's only used the applied force. Then you've got, or suddenly said that it's half of the gravitational force. Either one I would have accepted. Brad suggests that the normal force in the diagram is 25 newtons. All he's worked out is a component of the applied force in the vertical direction. Not enough. Mark suggests that the normal force is 100 newtons, so he hasn't considered the subtraction of this 25 newtons. He's only worried about he's basically said the normal is exactly opposite to the gravitational force. We've got Matt and Brad and they're fishing. Matthew hooks a fish on the surface of the water, and after reeling it closer, it yanked vertically upward with an acceleration given. As a result of pulling too hard, the fishing line snapped, allowing the fish to escape. Bradley estimated that the mass of the fish was, the resultant force on the fish would be whatever. So let's do that calculation. Force resultant is equal to mass times acceleration. Mass of the fish, acceleration of the fish, 5,4 newtons upward. Don't forget, it wanted resultant force. I should have a direction. If the breaking strain of Matthew's line is 25 newtons, show that the line would have snapped as the fish was done. So force resultant is equal to force applied. So basically he's going to apply a yank up there, and then there's going to be a gravitational force acting downwards. So the resultant force is the yank minus the gravitational force, which is going to be, we know the force resultant, we've just calculated it, 5,4 is equal to the applied force minus the gravitational force, which is 2,7 times by 9,8, and that is 26,46. And then my answer turns out to be equal to 31,86 newtons. 31,86 newtons is greater than 25 newtons, therefore it breaks. Now we have to state Newton's second law. So when you state Newton's second law, if net force is applied to an object, the object will accelerate. Don't forget in the direction of the force. I know it's not in your notes, you need to modify your notes. The acceleration is directly proportional to the net force and inversely proportional to the mass of the object. State the tension in rope A. It's the same rope. So rope A will be 950 newtons, and because it's a tension, it has a direction, it is upwards, because it is pulling away from the 50 kilograms. Draw two separate labeled free body diagrams for each of the boxes as they are being accelerated. So the one has tension A. This one is tension B. This is the 50 kilogram, by the way. And also it has its weight. Both of those. So it has two forces over there, and then with the 20 kilogram, you've got tension B and a weight. And then it says calculate the acceleration of the system as well as the tension. So let's go. Force resultant is equal to big, which is tension A, minus small, tension B, minus weight. I consider each block separately. I don't now try and also consider the block of the the weight of the 20 kilogram, because that's going to be incorporated in this tension in rope B. I then say 50A is equal to 950 minus the tension in B, which I do not know, minus the weight is going to be 50 times by 9,8, which is going to equal to 490. On the other side, what have I got? I've got 20A, force resultant, is equal to big minus small. Whole system's moving up, so TB minus 20 times 9,8. When I rearrange those, I'll get that TB is equal to 460 minus 50A, and over here TB is equal to 20A minus 196. So the next thing that we need to do is we need to make those equal to each other and solve. A is going to turn out to be 3,77 meters per second squared. That's just by making that equal to that. And then when you substitute in, your tension in row B is going to be 20 times by 3,77 plus 196. And that is equal to 271,43 newtons. Last question, we've got this rolling ball and it's released on a frictionless slope 5 meters above the surface as shown. Once it reaches the bottom of the slope, this 3 kilogram ball maintains a constant speed. In other words, the forces are all balanced until it reaches the rough surface with the coefficient of friction. Sketch a fully labeled free body diagram of all the forces while it is moving on the rough surface, not on the smooth surface. So what you're going to have is you're going to have, obviously if it's all the forces, you're going to put in the weight or the gravitational force, you're going to put in the normal. They say the horizontal forces, then you don't put all of those in. All the forces were balanced on this 3 kilogram ball. So there was nothing to the left and nothing to the right because it was going at constant velocity. So the only other force that's now been added is a frictional force, which will slow it down. And then it says calculate the average frictional force while it's on that surface. Frictional force is equal to mu Fn, which is equal to 0,3 multiplied by 3 kilograms multiplied by 9,8, and I am left with 8,82 newtons. Again, they haven't said magnitude, so I need to put direction, and here I did penalize you if you didn't put direction.